Okay. Okay, I think we're recording. Um, so I think that means we can start. Um, Thanks for coming in person. Thanks to those of you online. I hope that this is a helpful experience for all of you. So my name's Kelly Street. I'm an assistant professor of biostatistics. This will be my third year at USC that we are entering. I've been coding in R for at least 12 years now. Um, so I have a lot of experience with R, but I definitely remember what it was like to be a beginner. And so I tried to, keep that in mind when designing the curriculum for this boot camp. This boot camp is really geared towards beginners, people who have never used R before. And I hope that you get a lot out of it. But, obviously there's a lot that I can't teach you in just 3 hours over the course of 3 days. R is really, it's a language. It's a programming language, but it's like trying to learn any other language. You need to actually practice it and do it in order to become fluent. And so I can sort of point you at some resources and maybe get you started with some basic grammar and things. But if you want to become proficient in R, you have to practice it. You have to work at it and do it sort of repetitively over the course of a long time. So yeah, that's my intro. I think R is really fantastic for a number of reasons. One, it's open source, so you don't have to, if you wanted to get a new function in like Stata or SAS or something, you'd have to email the people who are in charge of it and hope that they agree that like this would be a useful thing to add to the language. Whereas in R, if you want something
Probably
new, you can
controlling
just
for like
make
safety.
it
I've done those
make it
PHS
available.
forms around.
Is there a question in the Zoom? Okay, somebody was talking there. Um, R is open source. Everybody can see what it's doing. And if you want some new functionality, you can go out and make it yourself. And the packaging system is really, really great. You can just easily pull any other, code that other people have generated uh, and try out the latest and greatest methods on your own data. So big fan of R. Definitely I think one of the best programming languages, especially for statistical analysis. So let's get going because we've got a lot of material to get through today. Um, you need to start by downloading R. So I realized we didn't put this in the flyer and we should have. This should have been a prerequisite for the boot camp. But if you Google CRAN, C-R-A-N, as in the first part of cranberry, you should get the Comprehensive R Archive Network. This is sort of the foundation that supports the basic R programming language. And if you click on that link, you can see I've done this all recently. You can download R for whatever your preferred, whatever operating system you're on. So I'm on Mac OS. So I would click download R for Mac OS. And then I would pick this first one because I'm on an M1 chip, but depending on what type of Oh, no, actually, I'm on an Intel chip. This is an old laptop. I would do this one. But for those of you with newer Macs, you would want the first one. Anyway, and for Windows and Linux, obviously, you want the other two. This will give you the R programming language. And that's a necessary step, but it's not everything you need. So what this gives you is basically access to coding in R, but it doesn't have a built-in way of doing that coding. Or rather, it does, it's just not very good. And so the second thing that we want to install is RStudio. And so once again, if you just Google RStudio, it should be the top result. I recommend RStudio Desktop rather than Cloud or any of the other possible things. This is just an app that can live on your desktop. If you go there, Posit, by the way, is the company that owns RStudio. They used to be called RStudio, and this was the only thing they did, but now they've sort of branched out to other languages as well because they're really good at making these IDEs. But yeah, go to download RStudio Desktop. Um, If you haven't already, they will instruct you on how to install R. So you need to have the programming language installed. And then you can install R Studio and it'll, I think, detect what operating system you're on. You can click download R Studio Desktop and go through the installation process. I'm going to pause for a minute here just to give everybody a chance to actually do those things, but hopefully you can get through that relatively quickly and end up with something like this. So this is what RStudio looks like when you open it. You won't have this upper left panel, but you will have sort of, it'll look sort of like this with a big console, an environment, and then a plotting window, or possibly files. Oh, and you should have a more recent version of R because this one's slightly out of date. A new version of R comes out every 6 months. I think we're on 4.4.1. Yeah, 4.4.1.
Wait, sorry. Can you go back to downloading R? What button am I supposed to click again? I clicked on the download R for Mac OS and then what am I supposed to click on that page again?
Whichever version of R is appropriate for your
Oh, okay,
computer.
thank you.
So if you've got a newer Mac, do the first one. And if you've got an older Mac from like 2020 or earlier, do the Intel chip one. Yeah. On the Posit website for installing RStudio, there's also a link directly to that CRAN site that we were just on. CRAN is also the host of of a lot of different R packages, and it's very easy to install packages from CRAN.
Hey, I have a question. I I have a version to RStudio. Actually, was in this boot camp like last year, but I forgot everything I learned. So, the R I have 4.3.1. Is that going to be okay, or should I?
Yeah.
Okay.
Everything everything we're doing in this boot camp, it really doesn't matter which version you have. Basically anything 1.0 or later will work.
Okay, awesome. Thank you.
Mhm. Okay. One other thing I'm going to point you at is the USC Biostats R Bootcamp GitHub page. This is where all the materials for this boot camp, not only this year, but in years past, is collected. So there's a lot of stuff here. There used to be multiple tracks. There used to be projects. We had, this has taken a lot of different forms over the years. But we don't have, it's only 3 hours over the course of 3 days in its current iteration. So we don't have a lot of time to go through a whole lot of stuff. Is there a question? Could you share the folder, please? This is, I can give you the link, which is that, github.com/USC Biostats/R Bootcamp. And this has got all the materials, like I said, for the previous versions. And today, I'm just going to be working off of some of the day one materials. Specifically, there's a script called demo.r. You don't need to get this. And in fact, I would encourage you to follow along with what I'm doing just by typing at your console. But if you want it later, demo.r is the script that I'm going to be going through today. Okay, so let's actually do some coding now. Like I said, this is what RStudio looks like when you open it. If you create a new R script up
Hi,
at the top.
sorry, apologies for interrupting, but is it okay if my R Studio I downloaded from the webpage that you shared with us is like a very old looking version? Like it looks like something from like the late 90s.
It's probably just a configuration, like
Oh,
a appearance thing. So if you go to tools under global options, you can totally change the appearance. And I actually really hate this like bright white on gray appearance. So I almost always do this and switch to a darker theme.
Okay, in this version, there is no tools tab, so I am
Oh,
just gonna go with it then as is.
okay. Then
Okay.
yeah,
It
you don't
sounds
have.
like she may possibly be running just R instead of RStudio.
Oh yeah, that's a good point. Is it actually RStudio in the top left or is it R?
It says R view R console.
Yeah. So you have the built-in editor for R. So it sounds like you downloaded R and
Mm-hmm.
implemented that, but then didn't install RStudio, which is the program we're going to use to actually do the coding.
Okay, let me give it another go. I'll follow along. Thank you.
Mm-hmm. Okay. Very quickly, RStudio is, I think, the best way to interact with the R programming language. Your starting point should be the bottom left. This is the console. And this is where you can type code directly and have it execute immediately. So, anything that I type down here will be treated as code and it will be executed immediately. If I type just some random stuff, it'll probably throw an error. Yes. But yeah, this is the console. The scripting window up here is for writing out code that doesn't get immediately run. So if I, also run some stuff up here and hit enter a few times, it's basically just a text editor. There was no error message when I hit enter here, right? Because all I did was type some text. It's a text editor where you can prepare your code, and it's actually got some smart context stuff that lets you know, hey, RStudio might be able to find an error for you before you even run the code, and that can be really helpful. Okay, so with that said, I'm going to jump over to my demo.r script. A lot of this is based on a really great cheat sheet. So there's this base R cheat sheet, and I gave a link to it up here at the top of the script, which just has, in sort of like poster format, a lot of the things that I'm going to go over today in very, very compressed format. So I'm going to try to expand on all of these concepts a little bit. All right. And the first, like, simplest and most basic thing you can do with R is to treat it as a calculator. Like I said, highly, highly encourage you to actually, whenever I'm showing things on my screen, follow along by typing them into your console. It's not, like shocking that R can do basic calculator functions, but I think it's an important starting point for learning what R is capable of. This is the basic structure of input and output for commands. So I typed 1 + 1, it said 2 was the answer. This little 1 over here is basically just a line indicator. It's like this is the first line of output, or rather this is the first item of output. It's going to continue to do that after basically all of these. There's each of these outputs is only one element long. It's just a single number. So that's why it keeps saying 1. But yeah, basically all of the stuff you can do on a scientific calculator, you can do in R. It's got basic order of operations. You can use parentheses if you want to, force a particular order. And yeah, that's really all I need to say on the subject. Most of the time, you won't be using R for this, but it's an important thing to know because it sort of gives you a sense for how R is interpreting the input that you give it. The power operator, so this is 3 to the power of 10. And then we start to get into functions. So we've got a square root function. we've got an absolute value function, we've got a log function, and if you want, you can even change that to say base 10 log by specifying base equals 10. Functions are going to be the primary way that you interact with R. Everything that's worth doing in R is part of a function. There are very few times, I think anything you do, anything you want to do that has any actual real world meaning is going to require functions. And that's one of the fundamental building blocks of R is the functions and the associated documentation. And so I didn't actually do it until later, but I'm going to do it in the script, but I'm going to do it right now. If you go to your console and type a question mark and then immediately follow it up with the name of a function, so I'm doing log here, it'll open up the help documentation for that function. So over here on the right, I've opened up the logarithms and exponentials help documentation. And so it explains a few basic functions: log, log b, log 10, log 2, log 1p, exp, and expml. And in all cases, they take as input a number, which they call x. And in some of those cases, there's a second argument called base, and you can supply the base for the logarithm. For log 10, you don't need to do that because it's log base 10. Same for log 2. So those only take one input. And then there's a little explanation of the different inputs, some details about how the calculation is done, and what the output value is. And then at the end of every help page, there will be some examples that show you just some valid code that you can use that will run those functions. It's a requirement for R packages that every function be documented. So you can always do this with any function. Also, will we have access to this recording? I hope so, but if you weren't on here earlier, I don't know, because this is not the same setup that we've had in years past. However, recordings from previous years are available on YouTube. Just search USC Biostats. We've got trigonometric functions. They're in radians, so 1 means 1 radian, not 1 degree. Oh yeah, this is a fun one. So I've included in a few different places in this demo script intentionally bad code. Some of the code is unintentionally bad, but this one was intentional. What's the problem with this cosine 2 pi?
You're missing the multiplier, right?
Yep, exactly. Exactly. Now it's 2 times pi, which is the correct way of saying 2. Yeah. The 2 pi is like a common mathematical thing, but R doesn't know that putting a number next to a variable means multiplication. You need to explicitly say, do the multiplication here. If we do that, we get the correct answer. Tangent. I'm also using a built-in, I should point out that pi is just a built-in constant in R. So you always have access to pi if you need it as a number. Some other weird things with numbers. R has infinity and negative infinity as possible values. And unfortunately, if you divide a positive number by 0, it gives you infinity rather than the thing that it should give you, which is not a number. But if you divide 0 by 0, you get not a number. These are some just weird special cases that it's worth knowing about. And then one more math function. For those of you who have taken a stats class before, PT is the function for calculating probabilities on a t-distribution. So let's say you were doing some statistics work and you calculated a z-score of, or a t-statistic of negative 2.4, and you wanted to know what's the area to the left of that on a t-distribution with 15 degrees of freedom, you can use this PT function to calculate that exactly, and there it is. I'll point out that it's always the area to the left. So if I had got a statistic of positive 2.4 and done the same thing, we'd get an answer of 0.98, which is just 1 minus that previous number. So useful for those of you doing statistics. This is something that comes up a lot. And unfortunately, in a lot of statistics classes, they still teach you to like go to the back of the textbook and look something up in a table. And like I said earlier, you can do question mark the name of a function, so in this case PT, to get all of the help documentation. And in this case, there's actually a lot of different functions. So you can calculate the density, the probability, quantiles, and you can generate random samples from a t-distribution. There's also all of these things for a normal distribution. It uses the same 4 first letters, D, P, Q, and R, to basically tell you about a normal distribution. Could you show how you are running the single line of code? Oh yeah, sorry, I forgot to mention that. I'm just hitting Command Enter. If you're on Windows, that's Control Enter, but on a Mac, it's Command Enter. So if my cursor is on this line, line 35, I hit Command Enter, and it automatically runs it in the console. Highly recommend making use of that. I spend almost all of my time in this upper left pane. I rarely type code by hand into the console. Good question. Sorry, I skipped over that. All right. That's math. Question. How do you find all the functions? Google. If there's a particular thing you want to do, just Google how to do this in R. A lot of programming is just Googling. In general, I don't sit down and like learn a whole bunch of functions. I just learn the one that I need to do a specific task. So this boot camp is kind of unique for those of you participating, because this is really the one time that you're just going to get a whole bunch of functions and different things thrown at you. In the course of your research, in the course of your actual coursework and then actual work, you'll more generally have specific problems that you're working on or specific questions that you're interested in answering. And if you just go to Google, how to calculate the probabilities of a t-distribution in R, it'll generally give you something helpful. So calculate distribution in R. Yeah, points you at the dt function, which is in the same family that I was just pointing at. There's pt, which is the function that I was actually using. Where was that cheat sheet you showed? The link for it is at the top of the demo.r script. It's from RStudio. RStudio has a collection of cheat sheets that are very good. All right. So we've seen how to use R as a calculator, which is great, but it really doesn't unlock the potential of R. There's a lot more we can do here. And we start to sort of unlock the programming aspect of R when we're talking about variables. So variables are a way to assign values a name and then manipulate those values. And the way that they work is with this operator, this left arrow assignment operator. Yeah. I'm often going to pronounce this as gets. So if I was reading this line of code, I would say X gets 3. But what this line of code is doing is it's creating a new variable called X, and it's assigning the value 3. So I'm going to run that. And what you'll see happen is it added a new thing in the top right pane, which is our environment. We now have a value called X. And that's just a variable that we created. We could have called it anything. If I print it, this is going to throw an error. This is an error that you will run into all the time. I guarantee it. I'm also just like, I included all of these bad lines of code because I want you to be comfortable getting errors in R. You will get errors. I get errors all the time. I've probably gotten like a million errors over the course of my lifetime coding in R. It's totally fine. Like if you're in RStudio, the guardrails are up. You can't do anything too terrible. Like everything's fine. The problem here is that I used a capital X. Object capital X not found. I'm just pointing out the fact that R is case sensitive. So if we wanted to fix that, I would do a lowercase x. If I print it now, we see we get the value 3, which is what we assigned it. You also can just sort of skip the print part. If you just type X into the console and hit enter, it'll tell you the value of that variable. And so this is very helpful whenever you want to know the value of a variable. And maybe you've got too many variables in your environment to look in this top right. I can manipulate, I can change or update the values. So here I'm saying X gets X plus 2 and assigning it. And you'll see the value in my top right change to a 5. If we print it on the console, again, tells us that the value is 5. So variables, very helpful, kind of, similar to algebra. You can assign names to numbers. You can also combine multiple values into a single vector quantity. And this is an important aspect of R and just sort of math in general. You do that with the C function. C stands for concatenate or combine, depending on who you ask. But if I do C 3642, you can see that gives me a little row of output. So all of the outputs we've seen before have been just a single value, whereas this one has 4 values, and it's just the 4 that I indicated, 3642. And we can also assign variables to vectors of values. So here I'm creating a new variable y, and I'm giving it a value of 3642, that length 4 vector that I showed earlier. How to type the arrow. The arrow is a less than symbol and a hyphen. Oh, sorry.
No, I just wanted to throw out, I did at first mess up by typing the arrow the opposite way with a dash and a greater than symbol, and that does not work.
Well, it can work actually if
Okay.
if you do it in the opposite order. It's just really weird. So nobody does it this way, but this would do the same thing.
Oh, okay, cool.
Yeah. So it is possible to do a right arrow, but nobody ever does it. People only do left arrows. It's just sort of a convention. One other question in the chat. Is there a way to go back to the previous value if you overwrite it? No. Whenever you print something in the console like that, I can recover that value. There's a built-in thing called .last.value. And so if you type that, it will tell you what the previous output was. So let's say I typed C3642, and then I just entered it to the console. And I realized after the fact, oh, I wanted to save that value. I actually really needed that for the thing I'm doing. I can say y gets dot last dot value, and it'll pull whatever the most recent output was to the console. Oh boy, we're running late. Okay. Some functions that you can use on vectors include length, tells you the length of a vector, mean and standard deviation, give you the mean and standard deviation of a vector. Both super helpful. Like all of these are things that you're going to need pretty regularly, I would imagine. There's also variance, var, gives you the variance, which is just the standard deviation squared. Okay. Math works very much the same way, except when it's on a vector, it does the math to every element in the vector. So y is a vector 3, 6, 4, 2. And if I do y plus 2, I get 5, 8, 6, 4, which is that previous vector plus 2 to every element. Same with square root, takes the square root of every element in the vector. You can also sort the vector using the sort function, 2, 3, 4, 6. But notice the actual value in y is unchanged. I haven't overwritten it. If I wanted y to become the sorted version of y, I'd say y gets sort y. But I don't want that. Okay. This vector was kind of cumbersome to create. I had to type C parentheses 3, 6, 4, 2 with commas in between. You can quickly create vectors of integers using the colon. The colon means all integers between these two. And so if I say 1 colon 10, and I run that, I get all of the integers between 1 and 10. And this is a quick way to create useful vectors of integers. The generalized form of that is the seq function for sequence. So I could also do 1 to 10 by doing seq 1 comma 10. It would create the same vector. But more generally, you can give it any starting point, any ending point, and by. So how many, every 5th element, every 10th element, whatever you want to be counting by. So I could do all multiples of 5 between 5 and 100 by doing this. Or, if I was interested in studying election years from 1900 to 2024, I could get that entire list using this command. Rep is another handy one for creating vectors. Is there a way to create a comment in the script editing window that can't be run as code? Yes. The way that you do comments is with the # or the hashtag, whatever you want to call it. But this is now a comment. I've been doing it with my section headings. They'll start with that sign. So these are all just comments, not code. I highly recommend that you comment your code liberally. Comment everything so that you know what you were doing when you wrote that code, because it's a lot easier to read English, to read written language than it is to read code. Rep is another super helpful one for creating sequences, particularly repetitive sequences. So rep is short for repeat. If I say rep 0, 100, what that's going to do is it's going to repeat the number 0 100 times. And so that gave me a vector of length 100 that's just a whole bunch of zeros repeated over and over again. It takes additional input optionally called each or times. If I say rep 1 to 3 each equals 20, it's going to repeat each of those things 20 times. So now I've got a vector of length 60. It's 21s followed by 22s followed by 23s. And if I say rep 1 to 3 times equals 20, it's going to do something similar, but it's going to take the original vector 1 to 1, 2, 3, and it's going to repeat it 20 times. So now I've got 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. We've also seen the T and norm distribution functions. If I want to quickly create a vector of random normals from a standard normal distribution, we can use the R norm function. And so just like the T distribution, this is part of that family DPQR. And if I just say R norm 100, what that's going to do is it's going to generate 100 random draws from a standard normal distribution. And so I can assign that to X. This is overwriting the previous value of X, which was 5. It's now a numeric vector of length 100, and it's just a bunch of random normal numbers. If you want to see what the distribution looks like, you can use hist, which is the histogram function, to plot a nice little histogram over here. This is not, I'm not going to talk about plotting too much today because tomorrow is about plotting, but that's a useful one that I think you should be using all the time. As we've seen before, functions can take multiple inputs. So I can also change the mean and standard deviation to this R norm function. If I do that and plot the histogram, we see that now we're centered at 10 and we have a much wider variance than we did before. The sample function is also extremely useful for basically drawing things at random. And this is really helpful when you're doing non-parametric statistics, or when you want to say split your data into a training and testing set, but you want to split them at random, you would use the sample function. And so this first one is just saying sample from the numbers 1 to 10, give me 5 of them at random. So half of those numbers. And if I run it once, I get 3, 10, 8, 2, 5, just randomly picked 5 of them. If I run it again, I get a completely new answer. You can run it as many times as you like, and you'll get completely different, well, not all the time because there's a limited number of possibilities, but it will do it at random again every time. This is the same as saying sample 1:10. From this set, we want to sample 5 things. Down here, let's say that for whatever reason, we're only interested in the numbers 0, 5, and -5. We can sample from that set one time. Or if we wanted to create a long string of random values from that set, we could sample from it 50 times, but this is going to throw an error. And it says, cannot take a sample larger than the population when replace equals false. So if you look at the help for the sample function, you'll see that replace equals false is actually a default value. So X and size don't have any defaults, but replace equals false and prob equals null. These are default values that are going to be given to the function unless you explicitly replace them. So if we want to actually do this, we want to sample 50 times from something that only has 3 elements, we need to say replace equals true and overwrite that default value. And then we can do it. And it creates a vector of 5s and -5s and 0s that are all just sort of randomly distributed. Going to pause for questions there.
Just double checking the replace is to is it for when how your sample size is smaller than the number that you want to write out?
It's for sampling with replacement, basically. So up here, we were sampling, up here replace equals false. So every time we run this line of code, we get 5 distinct numbers. We could never draw the number 7 twice. But if we were sampling with replacement, we could. We could draw the number 7 5 times. And so here we're sampling with replacement. And so yeah, I think you had it right. I think your understanding is correct, that basically it's necessary for times when you're trying to sample more than the complete list of possible options. And in other cases, it's optional.
Got it. Thank you so much.
Yeah. Okay. So I want to talk quickly about classes. This is something that I've sort of hinted at, but I haven't really talked about explicitly. So X is currently a vector of 100 random values, right? It has certain characteristics. Every object that exists in R has certain hidden characteristics, one of which is its class. And so if I say class of X, it's going to tell me numeric. It's saying X is a numeric type of object. And that's not surprising, right? It's a vector of numbers, so we would expect something like that. I'm going to do something different now. I'm going to assign a value of this in quotation marks to X. And that's totally allowed. If you look in your environment, you can see that X is now this in quotations. If I print it, it prints out just as is. And the class of X is now character. So character is what we call text or strings. These are called strings in a lot of other programming languages, including Python. But in R, they're called characters. So X is now a character that has a value of this. Almost all of the things that we've done with numbers, we can also do with characters. So here I'm just showing how we can use the sample function with an input of ABC. So I'm using the C function to combine the letters A, B, and C as characters. And we're going to sample one item from that list. So I got an A. I run it again, I get a B, run it again, got a B again, run it again, got an A again. But we're sampling from a list of characters the same way that we sampled from a vector of numbers earlier. Not everything that works with numbers also works with characters. For example, math. If I try to say X plus 2, that throws an error. Non-numeric argument to binary operator basically means you tried to do math with something that isn't compatible with math. Another type of object that we've seen earlier when we did replace equals true is these logical operators. So if I say X gets false in all caps, you can see that changes the color of the text. That's because false in all caps is a special value. And the class of X is now logical. And the same way that we can build, vectors of numbers and vectors of characters, we can also build vectors of logical values, which are just true or false. Some useful functions that you'll want to know. So I'm going to switch X now to a vector of character values, B, A, B, C. Maybe this is some data that you got from a collaborator or something. We can sort it the same way that you can sort a vector of numbers. When you sort a vector of characters, it sorts them in alphabetical order, not surprisingly. The table function is really helpful for counting up how many of each different value you've got. So it tells us here that we've got one A, two Bs, and one C. And the unique function will just return all of the different unique values, in this case BAC, in the order that they appear in the original vector. So the original vector was BABC, and that's why when we call unique, we get BAC, because it just picks out a new element every time that it sees it for the first time in the vector. And one other one that I want to mention really quick is a factor. So I'm just going to convert X. So X is our BABC character vector right now. I'm going to convert it to a factor with the factor function. And if I do class of X, we can see that it's now a factor. And if I print it, it now prints out without the quotation marks. Now it just says BABC, and it's got this extra line here that looks a little weird that says levels ABC. So the levels indicate all of the unique values that it can take on. This is really helpful for when you've got categorical variables. If the possible values are, green, red, and blue, a factor variable can be really helpful for encoding that. Okay, that's all I want to say about different types of classes. For the most part, we're going to be working with numbers, and a little bit with characters and logical. Okay. Super important thing that I really wanted to discuss, and I wish that we had more than 10 minutes left: indices and subsets. Indexing is super, super important in R, and it's how you basically pull out part of an object. So I'm going to create a long vector, long-ish vector here. Again, I'm just overwriting the value X because I don't care about the old one. But I'm going to make it a character vector of length 5, and it's just the letters A through E. And let's say for whatever reason, I wanted to pull out the first element of X. You can do that using these square brackets. And so X square bracket 1 square bracket will pull out the first element of X. And we know that that's an A. If you do this, you're going to get an error. The problem here is that I used parentheses. Parentheses are typically reserved for functions. Functions like C, that's a function. Class and factor, these are functions. So if I type X parentheses 2, it's going to look for a function called X. And it says, could not find function X. So there was no, it interpreted this as a function. If we want a subset, you really have to use the square brackets. And this will pull out the second element of X, which we know is a B. You can combine this with the stuff that we saw earlier. So 1:3 is a way of creating the vector 1, 2, 3. And if you use that as a subset, if we say X indexed by 1 to 3, it pulls out the first 3 elements, ABC. We can also explicitly create our own vector here, 1, 3, 5, and use that as an index for X, and it'll pull out ACE, the first, third, and fifth element. And you can also repeat elements. So if I say 1, 1, 1, it'll just give me AAA. And finally, indexing by logical values. Here I'm creating a long vector of trues and falses. So I went true, false, true, false, true. And if I use that long vector to subset X, it'll pull out all of the elements that correspond to true, which in this case is the first, third, and fifth. So once again, we get ACE. There's some weird non-standard stuff you can do with the minus operator. This means give me every element of X except the first one. So if I index X by -1, it gives me B, C, D, E. It drops the first one. If I do -1 to 3, I get an error. This one's intentionally wrong. Only zeros may be mixed with negative subscripts. So -1 to 3 does what you would expect. -1, 0, 1, 2, 3. However, this is a very confusing subscript because, first of all, there's no 0 element. It starts at 1. And second of all, we've told it to drop the first element, and then later we called for the first element. So there's a lot of things wrong with this. If what we had wanted to do was to drop the first 3 elements, we would need to put that 1 to 3 in parentheses. And then that would work. Then we would get D and E. That turns this into -1, -2, -3, which is exactly sort of what we would expect to happen. If we, if we index by -1, it drops the first element. If we index by the vector -1, -2, -3, it drops all 3 of those elements. And like I said earlier, there is no 0th element. If you do that, it gives you an empty character. It just says that basically the class of X is character, and it gives you an empty character. We can also do logical comparisons. And so this is very helpful. We saw earlier that we can subset by logical values, but logical comparisons really unlock the power of that. You might have wondered why you would ever subset by a logical value. This is why. So the equal equals means check for equality. This is a double equals sign operator, and it means check whether these two things are equal and return a true if they are and a false if they aren't. So if I say X equals C, I get false, false, true, false, false. It's what you'd expect, only the third element is equal to C. You can use that to subset X, and it's really helpful because you always end up with a vector that is the exact same length as X, as your input vector. So if I say X indexed by X equals C, we get just those elements of X that are equal to C. Similarly, I can do not equal to. This is a special character meaning not equal to. And it'll return the opposite, A, B, D, E. And if you want to compare to multiple values, there's this in operator, which is super weird looking, but it uses percents. This is saying return the values of X such that X is in the values A and E. And so not surprisingly, it's going to return A and E. Switching over to numeric vectors. Oh, question. Are there any functions that do that? Yes. There are dplyr functions that do subsetting, but I think it's easier to do it yourself. The square brackets are, in my opinion, much more intuitive, and they can really only mean subsetting. That's what the square brackets mean. Any other way that you try to do this is going to require more code and I think be less clear. So let's say Y is now a random vector of 100 random normal numbers. We can do comparisons like we did before. Now we can use greater than, less than, greater than or equal to, less than or equal to, things like that. So Y greater than 0 will give a long vector of trues and falses. If I subset Y to only those that are greater than 0, we can see we get all of these random numbers that are all indeed greater than 0. And if I want to overwrite Y to be just the positive values, I can do this and reassign Y using the left arrow operator to just those values that are greater than 0. And if we check the length, you can see we got 48 values greater than 0, which is about half of 100, which is how many random values we generated in the first place. So that makes sense. Occasionally, you will also see missing values. And in R, missing values are generally coded as NA. So I'm going to create this vector z, which is 1, 2, 3, 4, NA 5. This is something that happens in real data. In real world data, sometimes you have missing values, and the best way to code those in R is with an NA. There's this function is.na, which will check whether or not each value is NA. And you can see it returned true for this fifth element here, which is not surprising. And if we wanted to create a version of Z that is just the non-missing values, we could, again, use this exclamation point to say which of them are not NA. So the exclamation point, again, means not. It's the logical inverse. And so which values are not NA is going to be mostly true with 1 false in that fifth position. And we can subset Z by that to get just the values of Z that are not missing. Okay. I'm going to keep going, but I totally understand that this is supposed to end at 2. And if people have other things to get to, feel free. Are there any questions at this point? Yeah. Yeah, if you have to leave, don't worry about it. There are recorded versions of last year's content available online. Yes, we can. We will talk about working with, it might be a day 3 thing, but we'll talk about working with data in R for sure. Okay. Logic I want to talk about because it's super important. Yes, you can have as many missing value. Sorry for the people in the room, could you code more than one NA when you define Z? Yes. Obviously, it could be entirely missing values. You could have nothing but missing values, or you could have any number of missing values. Okay. Logical flow is really important, and it really leverages some of the stuff that we've talked about with logical values. So basically, what I want to talk about is if statements. So let's say X is a number. In this case, X is 0. I've got some lines of code here that look a little bit weird, but it says if X is greater than 2, print X is big. If I run that code, you can see that it ran in the console, but nothing happened. And that's because X is equal to 0. So this value here, X greater than 2, evaluated to false. And since that evaluated to false, then the code in between these curly braces did not get run. However, if we had set X equal to 3 and then run that code, we can again see in the console that the code ran, but this time it created some output that says X is big. So if statements are basically just a programmatic way to check if something is true. You can also include an attached else statement. So here I'm saying if X is greater than 2, print X is big, else print X is small. And in this case, you can see X is still equal to 3. So it's going to, if I run that, it's going to say X is big. If I reassign X to 0, we'll say X is small. Logical flow is a really powerful way of only running certain code when you want to. It's very important, I think, for programming. Importantly, this has to be a single value, right? X greater than 2 evaluates to false. If I say X, if I give X the value of 1 to 10, so X is now a vector, X greater than 2 is also a vector. False, false, true, 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 true. And so if I try to run this code, they'll give me an error. It says error, the condition has length greater than 1. That means the condition means this thing in the parentheses that needs to have length 1 has length greater than 1. If you want to do sort of an if-else type of logic on a vector, you can use this if-else function. So if-else x greater than 2, and then it takes two things. One is what to return if that's true, and the other is what to return if that's small, or if that's false. So x greater than 2 is a long vector of true and false. And if we run this code, we can see all of the trues got replaced with big, and all of the falses got replaced with small. So if else is a useful function for doing logic on a vector. Similarly, you can use for loops. So for loops are a common programming tool that allow you to do something repetitively. If you find yourself writing the same line of code more than 4 times, I think you should use some sort of loop, although most people who do R tend to avoid for loops, but the syntax is very easy and very similar to if statements. So here I'm creating a really simple loop that says for I. So I'm creating a variable I in 1 to 10. So 1 to 10, we've seen that's a vector of the integers 1 to 10. And basically what this is saying is create a variable called I and let it equal all of the values in this vector 1 to 10. And for each of those values, run whatever code is between these curly braces. And in this case, that's just a print statement, print the value of I. If I run that, you can see it looks like this. It ran that print statement 10 times. This is not a single output. This is actually 10 separate outputs. That's why they all have a 1 next to them. So it looped over this code 10 times. We can provide arbitrary vectors. So here I'm saying for x in 3, -5, 12, and 2. And we can provide arbitrary code. Here I'm just saying print x times 4. And you can see it does that for all 4 of those values. Importantly, this does change your environment. Notice I was added to my global environment after I ran the previous loop, and x is now equal to 2, which is the last value from this vector that I had given this for loop. So when you do for loops, it does change the value of a variable. While loops, I'm not going to talk about too much because they're generally not used, but same sort of thing. While some condition is true, so if x is 1, that obviously means x is less than 10. While that condition is true, print x and then overwrite it with x plus 1. And so that's going to do basically what you would expect. It's going to print a 1, and then it's going to add 1. And it's going to print a 2, and it's going to add 1. And so on and so forth until we get to 9, at which point we print the 9, and then we add 1, which makes x equal to 10. If we look in our environment, we can see that x is equal to 10, and that meant that this is, this is now false, so the while loop stopped running. The reason people don't use while loops is because it's very easy to get stuck in a situation like this. While x is greater than or equal to 10, print x and add 1. Logically, you can see the problem here. It's just going to keep going and never stop. It's printing, you can see how quickly it runs, right? We're already in 30,000 range, but this is just going to never stop running until I force it to stop by hitting the stop sign. The recommended way of doing a for loop in R is with this sapply function. And what it does is it takes a vector and it applies a function to every element of that vector. So this one's not particularly interesting because we can just do square root 1 to 10 and get the same thing. But this is sort of the more This is a straightforward example of how the sapply function works. This is one of the few times that you'll see a function used as input to another function. So here we want to apply the square root function to every element in this vector 1 to 10. We do that, we get the same output that we got before. Here I'm doing a similar thing with the absolute value function. And yeah, that's all I want to say about those. sapply is probably the correct way of doing a for loop, even if I think it's a little bit less intuitive. Okay. I'm just going to finish up by talking about data frames a little bit, and I'll stop after this. So R actually comes with some built-in data sets. If you type iris into the console and hit enter, you'll actually get something, even though we haven't created a value called iris. We haven't created that variable. This is a built-in data set. And it's a collection of data on iris flowers from 3 different species. And so you can see there's a species variable. I'm going to do something that looks a little weird. Iris gets iris. And that's just to force it to show up in our environment over here. So if we do that, then we've created a variable called iris and given it the value of this data set that already existed. And something really helpful you can do is just click on that in your environment, and it'll open up a new panel over here on the left that shows you sort of an Excel looking spreadsheet of that data frame. So iris is a data frame. You'll notice it's separate from our values. This is data, and it's 150 observations of 5 variables. Our variables are sepal length, sepal width, petal length, petal width. These are just different things you can measure on a flower, and then the species of flower. So these are all different species of irises. It's 50 from setosa, 50 from versicolor, and 50 from virginica.
Hey, sorry, I missed, how did you get it to make that table? Did you just double click on the?
Yeah, just
Oh.
click on it in the environment,
Okay, cool, thanks.
and it'll open a new tab over here on the left. I'm going to go back to my script here. So iris is an object, and its class is data.frame, which is the most common way of working with data in R. This str function is short for structure, and if you use that, it'll show you a little bit of a summary of the data set. So it says 150 observations of 5 variables, and it tells you what those variables are: sepal length, sepal width, and it tells you what type, numeric, 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 factor, and then it gives you sort of the first few values from that. And the most important thing that I want to mention here is subsetting. So subsetting a data set is very similar to subsetting a vector, except now we've got 2 dimensions. So when we subset a vector, it's just a 1-dimensional thing. It's only got the first element, the second element, the third element. But this iris data set is now a rectangular data frame, right? It's got 150 rows and 5 columns. And so if we want to subset this data frame, we need to use the square brackets again, but with a comma in those square brackets. And what the comma does is it separates the row index from the column index. And so if I say iris subset 1, comma, this is saying pull out the first row, and then there's nothing after the comma, which means give me all the columns. And so here, this is just the first observation from that iris data set. If we wanted the first column instead, we could do, again, nothing before the comma means give me all the rows, but then comma 1 means just the first column. And so there's that first column. which is the sepal length. And we can see it starts with that 5.1 value, which we saw in the first row earlier. We can use the colon notation that we saw earlier to pull out rows 3 through 7. So that's what we get here. If we only care about the first column, we can add a 1 after the comma, say iris 3 through 7, comma 1, and it'll just pull out those values from the first column. If we care about the first 2 columns, we can do 1 colon 2, and then we get sort of a sub rectangle of our larger rectangle. Importantly, there are multiple ways that you can access the columns. So we're often, when we're thinking about statistics, we're interested in pulling out particular variables from a data set. So if I pull out the first column with the square brackets, comma 1, that'll give me all 150 values from that first column. But I also could have done that with this special $ operator, which is how you can pull out variables by specific names. So if I say iris $sepal.length, it does the exact same thing. It pulls out that long vector of the sepal length values. Species does something similar. It pulls out the species variable, which we can see is a factor. This is one of those really good use cases for the factor class where we've got categorical data. And just like we saw before, these are basically just vectors now. So they've got things like length and class. In this case, sepal length is numeric and species is a factor. And a really important thing to note is that there's automatic tab completion. So if you just start typing iris $, it'll give you a list of possible things. And you can start typing any of them. Let's say petal. I was interested in petal length. I can just start typing petal and it'll sort of reduce the list of possibilities to things that are still reasonable guesses. So if I just type PET, I can go to petal length using the up and down arrows, navigate to the one that I want, hit enter, boom. There's also tab completion, so similar thing. If I type SPE for species, and then hit tab, it auto-completes to species. Highly, highly recommend using automatic completion just because we've seen already that R is case sensitive. And so tab completion is a way to make sure that you always get the capitalization right. Some functions that you can use on data frames, on rectangular data sets that you wouldn't have used before include dim. This is going to throw an error. Object of type built in is not subsettable. This is going to happen to you all the time. It happens to me all the time. The problem here is that I used square brackets when actually I wanted parentheses because dim is a function. Dim checks the dimensions. And so like we've already seen, it's 150 rows by 5 columns. N row and N col will tell you how many rows and how many columns you've got. And then summary is a really handy function that gives you sort of a little breakdown of each of the variables. So it gives you min, first quartile, median, mean, third quartile, and max for all of our numeric variables, and then a little breakdown of the different values for our categorical. I'm going to skip over the plotting because I'm going to do that tomorrow. And then here's just a way that we can combine some of the concepts that we've seen earlier. Like I said, if you want to pick a random subsample from a data set, the sample function is the best way to do that. So here, if I wanted to pull out 10 random observations from these 150, this is how I would do it. Sample from 150, 10 elements, which means without replacement, and then subset the rows of the iris data set by that random sample. If I do that, you can see I got observations 8, 79, 33, 37, 131, 117, 102, 75, 71, 34. Just 10 completely random observations from the data set. We can also subset by logical values. So I can subset by only those that have a sepal width greater than 3, or I can subset by only those observations where the species is equal to setosa. That's all I want to say here. You can also add new variables. So let's say I was interested, I'm pretty sure all of these measurements are in centimeters. Let's say I was interested in getting the sepal length in inches. You can do that by dividing by 2.54. So if I say iris dollar sepal length dot in, that's not something that exists. So it'll give me null, but I can assign it to iris dollar sepal length divided by 2.54. Run that, and you can see that it ran successfully. And if I now go back and look at my data set, we've added a new column, sepal.length.in, that gives the sepal length in inches. You can also just assign a single value if for some reason you wanted to create a column of ones. So I'm just going to say iris dollar new var gets 1. And again, if we go to our data set and scroll to the right, we see there's this new variable called new var, and it's just equal to 1 for every observation. So you can supplement your data set in that way. Okay, that's all I want to talk about today. Sorry for going over time. Didn't anticipate the time needed to actually install R and RStudio at the top of the bootcamp. So thanks for sticking around for those of you who did. I'm happy to stick around and answer questions for anybody who has questions. All right, thanks very much.
Hi, I do have a quick question.
Yeah.
How would you upload your own data set? And if your data set has a combination of like numbers and words, for example, if it's a data set, but there's some nulls in there, how would you go about working with the data?
So a lot of the things that we just showed about working with data frames is how I would work with it. But you can read data sets into R from the environment panel. I think it's a little bit too big to see right now. Yeah, there's an import dataset function. And so if you've got like a CSV, or if you've got an Excel spreadsheet, or you've got some of these other formats for datasets, you can import them into R, basically using a drop-down menu. And I think that's generally the easiest way to do it. You can also do it with code, but I highly recommend using the drop-down menu.
All right, thank you.
And we will talk more about how to work with data over the next 2 days of the bootcamp.
Thank you. See you tomorrow.
All right, I'm going to stop the recording.